Hi students, welcome back to this tutorial. In this video, we can discuss about a direct conversion method for converting binary number to its hexadecimal equivalent form and also for converting the hexadecimal number to its binary equivalent form. Okay, so based on our previous discussions, we can either follow this particular method for converting binary to its hexadecimal form. What is it? This one. That means if we are given with a binary number, we can convert that number to its decimal equivalent first. Then convert that decimal to its hexadecimal form. Right? So consider one example. So this is the given binary number. We can convert this into our decimal form. Then we'll get 16 as the decimal equivalent of this given binary number. Right? So after this, we can convert this 16 in decimal to hexadecimal form. Okay, then we get the value, this 10 in base 16. Okay, we can follow this method for converting binary to hexadecimal form. But this one is very lengthy and time consuming procedure. So here we can learn a direct conversion method which is very simple while comparing with this particular sequence of conversion procedure. Okay, for that we need to identify the relation between the bases. Here we want to convert binary to hexadecimal. So consider the bases. The binary base is 2, the hexadecimal base is 16. And we can generate a relation between these two bases like this. 16 can be represented as 2 to the power 4. Right? Okay, so based on this relation, here we can implement one table. Once more, in binary, we can represent two values. What are they? 0 and 1. And in hexadecimal, we can total 16 different values are there. What are they? 0 to 9. After that, the remaining 6 values, 10 to 15, represented using alphabets, capital letters A, B, C, D, E, and F. So, this is the digits or symbols available in hexadecimal number system. Okay, total 16 different symbols. So based on this relation, here we can generate one table. Okay, that generate a relation or that map hexadecimal value with the corresponding binary values. So here we want to list all the powers of 2 which is less than this power 4. So what are the powers? 2 to the power 3, 2 to the power 2, 2 to the power 1, 2 to the power 0. Okay, here 16 is 2 to the power 4. So here we want to list all the powers, all the positive powers of 2 which is less than this power 4. So these are the powers of 2 here and listed like this from higher to lower. 2 cube, 2 square, 2 raised to 1, 2 raised to 0. And its corresponding values are 8, 4, 2 and 1. Right? So, using this particular positional values, we can generate or we can identify the binary equivalent of each and every hexadecimal symbols listed here. So, the first one, 0, and 0 means here we don't want to make any position with value 1. So, full of zeros. And for hexadecimal 1, the corresponding binary is 0, 0, 0 and at this particular position make value 1. And for 2, here it is 0, 0. 8 position at position 8 it is 0, at position 4 it is 0 and at position 1 it is 1 and at position 1 it is again 0. So for 3, how to get 3? 2 plus 1 is 3. So here it is the binary equivalent of hexadecimal 3 is 0, 0, 1, 1. 2 position and 1th position. It contains value 1 and the remaining kept with value 0s. And hexadecimal value 4. The binary equivalent is here 4 is directly available at this position. So 0, 1, 0, 0. And 5. 5 means 4 plus 1 is 5. So 0, 1, 0, 1. And 6. 6 means 4 plus 2 is 6. So 0, 1, 1, 0. At position 4 and at position 2, we want to set the value 1 and the remaining positions with value 0. And 7. 7 means 4 plus 2 plus 1. So 0, 1, 1, 1. And the next symbol in this hexadecimal list is 8. How can we represent 8? This 8 is directly available at this position. So 8's binary equivalent is 1000. And for 9, 9 means 8 plus 1. We can generate 9 like this, 8 plus 1. So 1001. Okay. Next, the next symbol is after 9, we need 10, 11, 12, 13, 14 and 15. And this decimal equivalents 10, 11, 12, 13, 14 and 15 are represented in hexadecimal with alphabets A, B, C, D, E and F. So for A is actually equivalent to decimal 10. So how can we generate 10 here? 8 plus 2 is 10. So 1010. Next is 11. 11 in hexadecimal system is represented with the capital letter B, right? So 11 means 8 plus 2 plus 1. 10 plus 1. 8 plus 2 plus 1 is 11. So 1011. Next is 12. 12 is represented in hexadecimal with symbol capital C. So 12 means 8 plus 4 is 12. So 1100. Okay, then D. 13 is represented with letter D. The D 13 is obtained like this. That is 8 plus 4 is 12. 12 plus 1 is 13. That is 1101. Next is 14. 14 is represented with capital E. Okay, how can we generate this 14? This 8 plus 4 plus 2 is 14. That is why 1110. Next is decimal 15 is equivalent to capital F in hexadecimal. That 15 means 8 plus 4 plus 2 plus 1. So 1111. So this is the required table for our direct conversion from hexadecimal to binary as well as for converting binary to hexadecimal. Okay, so consider some example. So here we have one number in binary. We need to convert this into its hexadecimal equivalent form. So we need this particular table. We need to keep this table in your mind. This will help you to convert this binary to its hexadecimal form fastly. Okay. So the first task is to group this number. So here in this particular case for converting binary to hexadecimal system, in each group we need 4 bits. Because here each of these hexadecimal number is mapped with a binary equivalent that contain or that is represented using 4 bits. So here we need to here we need to group this given binary number from right to left, and each group must contains 4 bits. So group like this. The first group starting from left and proceed towards right. And the first group contains the bits 0, 1, 1, 1. And the second group contains 1, 0, 0, 1. So using this table, we can identify the hexadecimal equivalent of these group values. For this 1001, 1001 is 9. And 0111 is 7. So this is the hexadecimal equivalent of this given binary number. Right? Consider one more example. This is the given binary number. So we need to group these given number, and each group must contains 4 bits, and start the grouping from left and proceed towards start the grouping from right and proceed towards left. So the first group, second group, third group and the fourth group. But here we have a problem, that is here only 1 bit is left. So in that case we can append 30 to the left hand. Now we can make a full group here. Right? If necessary bits are not available in the left hand, then we can append the required number of zeros and make a full group like this. Okay, so this one is 0001 means, which is equivalent to hexadecimal 1, and this 1101 is equivalent to hexadecimal D, and this again 1101 equivalent to hexadecimal D. 0101 is equivalent to hexadecimal 5. 0100, which is equivalent to hexadecimal 4. So this is our hexadecimal equivalent of this given binary number. Okay. Okay, we can consider a new example. This is the given binary number. Okay, so using this table, we can convert easily to its hexadecimal equivalent form. So this is the given number. Start grouping from right side and proceed towards left. And each group must contain 4 bits. So group is like this, first group. But here only 2 bits remaining. So in that case, we can append 2 more 0 to the left hand and make a full group here. Okay, now we have 2 groups here. So this 0010 is 2, 1100 is 1100 is C. So this one is the hexadecimal equivalent of our given binary number. Okay. Now we can consider one example for the conversion of binary to hexadecimal, but the given number is a fractional number in binary. Okay. In this case, what we want to do, use the same table for converting this binary to hexadecimal. Okay. So this is the given number. So in case of this whole part, we can proceed like our previous examples. Start from right and proceed towards left, and each group must contain 4 bits. But in case of this fractional part, this is a different case. Here we need to proceed from this point, that is the point just after this decimal point, and proceed towards right. And here also we need to make different groups, and each group must contain 4 bits. Okay, so consider this case. So this is the first group. Consider the whole part alone. So this is the first group in the whole part, and here 2 bits remaining. So we need to append 2 more 0 to the left hand, make a full group like this. So now we can consider the fractional. Here after the fraction we have only 3 bits, 0, 1, 1. So we need to append 1 more 0 to the right hand here. In case of this fraction, we can append any number of 0 to the right hand. In case of this whole part, we can append any number of 0 to the left hand. Okay, so here it is a full group now. Now, using this table, we can match with the hexadecimal equivalent. 0010 means 2, 1101 means D in hexadecimal, and this 0110. 0110 is 6 in hexadecimal. So 2D.6 is the equivalent, hexadecimal equivalent of our given fractional binary number. Consider one more example. So here we need to convert this binary fractional number to its hexadecimal form. Okay, so this is the given number. So for the whole part, we need to make different groups, and each group must contain 4 bits. And we need to start from this point and proceed towards left. Okay, so this one is the first group, and here it is left with only 1 bit. What we want to do next, we need to append 3 more zeros to the left and make a full group like this. Okay, so this is the case of our whole part here. Next, consider the fractional part separately. Here we need to proceed from this point, that is the point just after this fraction or this decimal point, and proceed towards the right and make groups, and each group must contain 4 bits. So this is the first group of this fraction, and here also it is left with only 1 digit or 1 bit. So we need to append 3 more 0 to the right end. So it makes a full group here. Okay, so what are the now using this we can identify the hexadecimal equivalent. 0001 is equivalent with hexadecimal 1. This 0101 0101 is equivalent with hexadecimal 5. Next is this point. Next 0101 is again 5. This 1000 is 8. So this is the hexadecimal equivalent of our given number. Okay, next is the conversion of hexadecimal to its binary equivalent, which is very simple. We can use the same table for this conversion also, hexadecimal to binary conversion also. Okay, so this is the number given in hexadecimal form, and we want to convert this into its binary equivalent form. This 1 means 1 in hexadecimal is mapped with the binary equivalent 0001. So for this one, we can write 0001. And for this 5 in hexadecimal is mapped with the binary 0101. So 5 is replaced with 0101 here. And A is replaced with this 1010 and C is replaced with 1100. So this is the binary equivalent of our given hexadecimal number. We can directly simply write this with the help of this table. Okay. So next is the fractional number which is given in hexadecimal form. So use the same table. 1 means 0001, 0001 and this 5 means 0101 which is available from this table. 5 in hexadecimal is equivalent to 0101 is 1 in binary. Okay, next is the fraction point, the decimal point. Next 4. 4 means 0100, then 3 means 0011. So this is the binary equivalent of our given hexadecimal number. So the conversions are very easy and direct with the help of this table. Okay, try to understand or try to identify this equivalent hexadecimal and binary corresponding hexadecimal and binary value by practice. Okay, thank you.